So, I think anybody who's still here after 16 hours of this course deserves a reward, but I'm afraid having to listen to me one more hour is not necessarily the reward you deserve. But anyway, the end is in sight. So yesterday was already a degree harder than the previous times. Today I hope will be a little easier because I'm aiming now finally for the application to the questions about volumes of strata in moduli space of flat surfaces and Siegel-Veech constants. I will not go at all into the description of the geometry behind those numbers and the definitions because it would take too long and because I think many of you were in the conference lecture 2 weeks ago by Martin Müller, and if not, you'll just have to ask people in the audience, of which there are several who know it much better than I do, or look in the paper where it's written out, I hope, very clearly. But yesterday and today, as I said, I want to sort of now make everything come together, that all of the things we've done about the links between sums over partitions and modular forms now get actual applications to computing these numbers that people want in the theory of moduli spaces. So I'm going to have to repeat some things, which is probably just as well, because apparently yesterday I went quite fast. So let me remind you a little first the basic setup. So once again, I'll tell the Bloch-Okounkov theorem. We start with an abstract ring R, which is simply the free polynomial algebra on infinitely many variables Qi, graded by saying that the weight of Qk is k. So this becomes the sum of its graded pieces. Then that sits in a natural way in the set of all functions on partitions, simply by thinking of each Qk as a function of partitions. And I'll just remind you the two most important are Q2, which is a rather trivial function. Well, Q1 is really trivial, it's 0. Q1 of a partition is just the size of the partition shifted by 24th. And Q3 of lambda is the number that tells how that partition, thought of as an irreducible representation, behaves under the conjugacy class of transpositions. And therefore, if you think of coverings of a torus, but generically ramified, so here I have my torus, and here I've, let's say, if it's connected, the surface of some genus G, then I'll have k ramification points, where k will be 2G minus 2 ramification points. Actually, I should now call it n, because that's the notation Martin always uses. So I have n equals 2G minus 2 ramification points, but at each ramification point, you have the transposition in the symmetric group on D letters. So you have T in SD, and therefore the important thing of lambda, the important thing is this function ut of lambda. And because of that, it's the function, well, so I was going to remind you here also that we have this Q bracket function, which goes from arbitrary functions on P into power series, which sends an arbitrary function into the weighted average, sum f of lambda, q to the size of lambda, divided by the sum over lambda of simply q to the lambda. And then the Bloch-Okounkov theorem says that Rk maps under this Q bracket into quasimodular forms of weight k on SL2Z, and the one that we're particularly interested in for the coverings would be Q3 to the power n, which is 2G minus 2, and this would correspond to the covers. I mean, actually, this one corresponds to non-connected covers, and you have to do something with the logarithm, as I've explained in earlier things. So that's just to remind you why the Bloch-Okounkov theorem in general and the specific business of this Q average, average of a partition of a function on partitions over all partitions, is relevant for if you're counting covers. Now, for the Siegel-Veech and volumes business, as I mentioned very briefly yesterday, the coverings, so you have this space omega mg, the so-called flat surfaces. This typical element here is an isomorphism class consisting of a Riemann surface, so a curve, complex curve now of genus G, and a one form, so a holomorphic one form, not identically 0. So this thing, omega mg, is a fiber bundle over mg, over the usual moduli space. The fiber over a point is just c to the g minus 0, because it's a g-dimensional space of one forms. And one wants, it has a stratification according to how many zeros omega has. And omega always is n equals 2g minus 2g. Now I'm getting it completely wrong. It is, 2g minus 2 zeros, counting multiplicity, but you stratify according to the multiplicities of the series. And so the main stratum, which you can write as 1 to the n, that's the main stratum. Principal stratum is sort of the top dimensional one. That corresponds to omega has distinct zeros. So one wants the volume of that, and actually one wants the volume of all the others, and the methods that we developed apply to the others, but we don't yet have a complete asymptotic formula, and we're working on that now in further work with Martin Müller. So, but I'll talk about that. And then, as I said at the end of yesterday, very briefly, the idea is if you take a particular torus, like for instance C modulo Z plus ZI, and you consider all d to 1 coverings of that, so you get something that is a square-tiled surface. It has a lot of squares, d of them, and you glue them together, and then you get a surface which is a flat metric. So according to Gauss-Bonnet, it shouldn't have Euler characteristic 2g minus 2 minus 2g, but in fact it does, because there are singularities at these points. When you do the gluing, you can have the wrong number of 90 degrees coming together in a corner. And so what you get is special elements of omega mg, but you get a lot of them. If this d goes to infinity, for any fixed d you get a finite set, but they become denser and denser. And so if you just count the number in a given stratum or with given properties and look at the asymptotics of that, one knows that those are all proven theorems that will give you the volume and also these Siegel-Veech constants that I won't define at all, but I'll give the formulas for them later, and if you were at the lecture, you know what number you're seeing a formula for, and otherwise you're just seeing a pretty formula. So the idea is that the question which originally had to do with moduli spaces, volumes of things, maybe also intersection numbers, and many other related numbers, Lyapunov numbers, and so on, those things can rather surprisingly be computed in principle by reducing it to a finite combinatorial problem, which is understanding coverings of a certain kind, not just counting them, but something more detailed, and then look at the asymptotics as d goes to 1. But we already know that the straight counting function corresponds to this, at least this is for non-connected. And as I said, you have to make a generating function, take the log, and I'll come to that in a moment. So in today's lecture, now and after the pause, I want to explain, as I say, everything comes together, how we use the information we have. But first, I want to talk about this aspect of connected. And so I want to say something very general. This is now independent of everything that's gone before, but not of what comes after. So kind of a digression, if you want. If you already know what cumulants are, it's just something that you can sleep through. But it's a very pretty, completely general construction. Imagine that R and R prime be rings, by which I mean, decent rings. So they're, in my case, they'll be Q algebras. I want to be able to invert integers, and they're commutative and associative and have a 1, and they're nice rings. And I have a map from R to R prime, but it's simply a linear map, Q linear map. So it's not a homomorphism. So obviously the one I'm thinking of, and already the notation suggests that R might be this R, and the R prime might be the ring of quasimodular forms. So this ring, we know that M star tilde is the ring generated by 3 specific power series in Q. But here it could be any ring. And now I'm going to make something called the cumulants. So if you have a finite number of elements of the first ring, I'm going to define a thing in the second ring, which is called the cumulant, the nth cumulant, as follows. Well, first let me give examples. I'm going to give like 5 different definitions. So if I have just one, well, if there are no vertical lines, then of course it's just what it was. If there's one vertical line, this is the deviation. It's sometimes called the what is it sometimes called? The variance, I think, in statistics. What? Covariance? Covariance. Yeah, I can never remember these words. So it's the difference between the bracket of f times g and the product of the brackets of f and g. So in particular, it vanishes if and only if you have a ring homomorphism. I don't want to forget any of my... Wait, I just made notes carefully before the lecture so that I would not have to search for things, and I don't know where I put here. I don't want to forget any of the many formulas. So first I'll give the cases for n equals 1, 2, and 3. I said that, yeah, I didn't write everything. Commutative associated with unit Q algebras, yeah. I mean, it doesn't matter that there's a unit, but it's certainly commutative, yeah. The 1 I think I'll never use. Actually, if you have a 1 anywhere, it'll be 0. It'll be a trivial axiom, and we will never use that. Let me give the next one. So if I have 3, well, you can imagine it starts with FGH. Then you can have F times GH, but then by symmetry, it has to be G times FH and H times GF, or FG, it's commutative. And then the last term has a 2. So those are examples, and I can give several different definitions. So one definition, actually my preferred one, is inductive. If I have F, I could call it F0, but if I have a bunch of Fi's and I add 1, then it's like a derivation. If you think of that as differentiating, you can differentiate at any position. So you can insert the, obviously in the ith position, you can insert the F anywhere, and then you have to subtract one term, which is simply the bracket of F times the previous cumulant. So that's an inductive definition. A closed formula definition, if you like, a closed formula definition is alpha is a partition not of the number n, but of the set 1 up to n. So that means it's an unordered decomposition of the set into subsets. So for instance, if n is 5, then alpha could be 1 and 3, and 2 and 4 and 5. But you don't number the elements of the sets, and you don't number the sets. It's just a decomposition. Just like a decomposition partition of a number is an unordered splitting up into positive numbers, here a partition of a set is an unordered splitting of the set into disjoint subsets. So now if you have such a thing, then the formula is, if I could read my notes, it would be even better than if I couldn't read them. It's minus 1 to the size of alpha. So here the size of this alpha would be 2, because alpha is a set consisting of 2 elements, each of which happens to itself be a subset of n. And then here you'd have the size of alpha minus 1 factorial, and then you'd have the product, not the product, you have the product of the elements in that particular it's the sum, and here it's the product I can't read what I wrote. I know the answer, I just can't read what I wrote, and I won't get the notations right. Let me find the page on which I do this and copy it. I wrote it so quickly that I can't read it, which happens to me a lot, even when I write slowly. I'd written a sum, and I thought it can't be a product. So you take all of the elements of alpha, each of which is one of these sets, and then you take the product of the FA, A in that set A. So you'll check that that is exactly this with the right. So for instance, this is minus 1, and that's plus 1 times 2 factorial. Another formula is you can do it in reverse. You can multiply a bunch of Fn's. You see that you could invert all of this. So Fg, for instance, would be F slash cumulant G plus F times G. And similarly here, you can invert that. And then all the coefficients actually go away. So if you do it in the opposite order, you get the same thing. Alpha is 1 up to n. And then you have the product again, A and alpha. And then I just put F. Well, so I have to now temporarily label the elements of A something. And then I put FA1, the cumulant of the elements of A, for which there's no obvious notation. So that gives you several three different definitions. This is by inversion, but you can uniquely, once you know this, then of course you can solve for each. So each of these is a complete definition. And now comes the good definition. There's only one really good definition. And as usual, in mathematics, if you have anything combinatorial and you want to understand it, you try to write it in terms of a generating function. So the general rule is this. If you have a sum of elements in your ring, Fi, Now, if it's an infinite sum, you might say, what does it mean? And then one thing you could say is, let's say it's a graded ring, and the gradings of the Fi grow so that in any given degree, it becomes a finite sum, and you know what it means, and none of them should have grading 0, so that you can take this exponential. But then what you'll have is simply the sum. Well, it'll be the sum of the Fi's plus 1 over 2 factorial times the sum of the Fi Fj plus 1 over 3 factorial times the sum ijk of Fi Fj Fk. But of course, although I'm dividing by 6 factorial, if ij and k are different, then since the thing is symmetric, I'll actually get that term 6 times. And so you'll actually only see a generic cumulant once. And you'll see it less than once if it's got some duplication. A is an element of alpha, just like here. It's certainly not a subset of alpha. No, I wouldn't want a subset of alpha at all. Here, for instance, I gave an example. If n is 5, then alpha is a partition of the set 1, 2, 3, 4, 5. So typical would be alpha, which is 1, 3, and 2, 4, 5. And it is 2 elements, A1 and A2. So it's the set consisting of A1 and A2. So these are not subsets of alpha at all. They're subsets of the set from 1 to n, but they're elements of alpha. And therefore, I mean, the set of A in alpha is the disjoint. Well, here I can write like this. The disjoint union of the A and alpha is the set 1 up to n. But they're not subsets of alpha. Anyway, the examples up to 3 are supposed to make it clear, and it doesn't terribly matter. But the important thing is this. It tells you that these are the things that you get when you take the log, which, as we already know from both in my lectures and in Nicolaus, we saw many times, when you pass from a problem with non-connected things, like all coverings in possibly disconnected piece or all graphs, and you want just the connected part, you take the log of some generating function. So that's the yoga, and now let me apply it to the case that we wanted. So last time I introduced the partition function for the Bloch-Okounkov map, for the Bloch-Okounkov map. And so for that, the only thing that was a little of a nuisance is that I'd already had 2 different functions, qk. I had qk of lambda that I defined more than once, but about 2 weeks ago. But qk of lambda, I did an alternative description of a different invariant, and then they were related by a very simple formula that qk of lambda, but qk was better because qk was a homogeneous element. In this notation, it's much better to work with qk, so like q2 is the size of lambda minus a 24th. P2 in this case, beta k is just the coefficient of z to the k in z over 2 over sinh z over 2. So beta 2 is minus a 24th, which you see here. And it's important, however, to add that 24th because P1 wouldn't be homogeneous. But there's also an alternative notation, which is small p, which is the same normalization, the same shift, but you've included the beta k inside so that the pk is still homogeneous. And for the formulas I'm writing today, the most convenient. So big pk is never convenient because it's not homogeneous. These are equally convenient, but to get rid of the factorials, I'm going to use the small p's. So the partition function was a function phi of u, where u is an infinity tuple of indeterminates, phi of u1, u2, and it was simply written as e to this, well, x of the sum L from 1 to infinity. There is a q1, but since it's identically 0, I'll forget it. So when I use the PLs, I'll always have PL where L is at least 1. But L equals 1 is very uninteresting because L equals 1 is Q2, which is a stupid function. The interesting one is P2. So think of P2 as the one we care about. P2 is not exactly Q3 because there's a factor of 2, but up to a factor of 2, it's the same. OK, so now I take the generating function, sum x with the sum ULPL, and then I take its Q bracket. So, I mean, I wrote this last time, but I'll write it again. You can write this thing in 2 different ways. You can write this just by expanding the exponential. You can either say this is the sum n from 0 to infinity, 1 over n factorial, and then I have the nth power of the sum ULPL, which simply means that L1 from Ln are each greater than or equal to 1, and you have PL1 PLN Q times UL1 up to ULN. So that's simply by writing the exponential of anything as the sum 1 over n factorial times that thing to the nth power, and then the nth power of this sum is just the n independent sums. But that's not very convenient because you're repeating factors many times, and so usually you want to group it by putting these things, and so then you sum it like this, and then you'd have here P1 comma P1, P1 simply to the power n1 times P2 to the power n2, and so on, times U1 to the n1 over n1 factorial, U2 to the n2 over n2 factorial, etc. Okay, so this was the, and this I'll put a Q to remind us that this is the Q bracket, and I'll remind you in a minute that there's another one which I put in X, which is the X evaluation of that. But now I want to already, this corresponds to connected, not connected, disconnected things in general, and then the connected ones is defined almost exactly the same way, but maybe since it's kind of really playing the key role in what I'm doing, I'll write it out completely. So this is the sum n from 0 to infinity, 1 over n factorial times the sum L1 Ln greater than or equal to 1. But now you have PL1 cumulant, this new combination, and then UL1 up to ULN. And again, I can write this equivalently as the sum n1, n2, and so on, greater than or equal to 0. And then I have the cumulant where I've n1 p1s and n2 p2s, etc., and then the Q bracket again, and then U1 to the n1 over n1 factorial, same thing. And now, because of the yoga of cumulants that I already told you, it's immediate that if you know one of these functions, you know the other, because psi is just the log of u. But we want somehow the coefficients, and I somehow want to have both expansions. So people sometimes get confused about this. Whenever you have a series like this, there are two ways of doing it. They correspond to Witten's tau notation, and the other notation you can always pass easily back and forth, but it's very easy to get confused. So I thought I would write it out completely. So now I'll erase all of this. So that's the story we want, and we would really like to know everything. We would like to know completely the coefficients of this, a differential equation, a functional equation of either this or this. But unfortunately, we don't, as I said last time. But instead, we have this weakening, and I'll repeat that very briefly that I talked about yesterday, and maybe say one or two things that I didn't quite get around to saying yesterday. So I told you there's an evaluation map from quasi-modular forms, actually on any group. It has nothing to do with SL2Z. But I'll just do it for SL2Z. I mean, it makes essentially no difference. There are many ways to define this. Maybe I'll say the key point in a second. But for the moment, I'll just give the quick definition which I gave last time, which is that it's an algebra homomorphism. And it sends E4 and E6 just to x squared and x cubed. Well, here it'll be q because I'm always taking everything with coefficient in q. And for any modular form, as I said last time, if you have a modular form of any weight on SL2, so the weight is always even, then you'll send it to x to the power half the weight times the constant term. So delta, for instance, the Eisenstein series EK, E2k will always go to x to the k, delta will go to 0, and so on. But if you have a quasi-modular form, it's not just a monomial, in general be mixed, and in particular, E2 goes to x plus 12. Okay, the meaning of this is the following formula, but that I do want to copy, if I can find it, because I didn't write in my notes because it's too much of a pain to write down. The meaning of this is as follows, that if, let's say that the evaluation, I have some modular form f, and I get some polynomial in P. Then what you'll find is that if I take f of tau, where tau now goes to 0. So remember, f of tau originally is the sum Fourier expansion. That's the usual way to see a form. And so this is relevant. I mean, you can read off the coefficient when tau is large. So you usually think of tau going to I infinity. But now I can, if it were modular, I could just look what happens when you flip. Tau goes to -1/tau. And of course, at infinity, we know that f at infinity is a0 plus O of exponentially small. If tau is 100, I mean I times 100, then you'll have e to the minus 100, well, even times 2 pi. So it's incredibly small. So if you have a true modular form of some weight, let's say again 2k, then you see that f of -1/tau is, remember that for a true modular form, f of -1/tau is tau to the 2k f of tau, which means f of tau is 1/tau to the 2k. So if tau is very small, you get, wait a second. Now, it's always the problem. So people like, well, I think even Nicolas in his lecture, many others, whenever they write expanse over G, they tend to write things with h to the 2g minus 2. And I wanted to say this in public. They're all wrong. Everybody who writes that, I'm sorry, they always write it with h bar. And the h bar is to remind you that it's supposed to be quantum theory and Planck's constant. But actually, it should be h, because the h that they always use is actually 2 pi times another constant. And in quantum theory, h bar means the natural h over 2 pi. So here, what I want to do is I take I times h bar. I think I'm probably getting it wrong again. And then what I'll get, I'm not sure I'm going to be able to get this wrong, but the point is then the q becomes e to the minus h. Whereas in the people who do this usually write q is e to the minus h bar, but that's sort of killing the h bar. I won't even try to, I'll just put an epsilon, and there's a constant that it's written here, but I'll screw it up whatever I do. But within epsilon, actually I don't need 2k, I can just say if the weight is k, if f is any modular form of weight k, then this polynomial, as we saw, will have weight at most k over, no, I do want 2k, sorry, 2k, then it will be, well, the way that I've written it's 4 pi squared over h, which is also 2 pi over h bar, I guess, divided by h to the k. And that's, I'm not going to get it right. Whatever I do, I'm going to get it screwed up. But I think now it's correct. If I put here h bar, which is h over 2 pi, I believe this is true to all orders. So the point is, I was saying, I'm sorry, I said that poorly. If still doesn't look right. Something is wrong with this formula, even though I'm copying it. Yeah, it's h to the k, that's why. So remember that if I had a true modular form, forgetting 2 pi, I just said 2 pi I equal to 1, then p, if it's a modular form of weight 2k, then my formula for this polynomial was the constant term times x to the k. So this would be, but this thing is weight 2k, so when you apply f, it would grow like h to the 2k, because f of tau is f of -1/tau times tau to the 2k. So it would grow like h to the 2k, but this is h to the, that's right. This polynomial has degree k, so it starts, it would start h to the minus k. It was h to the k. It was completely okay. This starts like 1 over h to the k, so, and then you divide again, so it's like 1 over h to the 2k, which is the correct growth. But the point is that if it's quasimodular, then it doesn't satisfy that transformation law, so you can't immediately read off the growth, but you can read it off in various ways, and this is the correct formula if I didn't screw up. But anyway, the essential point is that that the evaluation polynomial gives you to the growth to all orders of the thing when you take f near the origin rather than near infinity. So f of I epsilon up to maybe a constant, some power of epsilon, but it's essentially a polynomial in 1 over epsilon, and that's the polynomial we take. If it were a modular form, it's just a single term, but in general, there are many. Since I said that so poorly, let me make amends by reminding you very briefly something we did yesterday. I took theta sub tau. I gave you yesterday, if I can find it in my notes, the evaluation polynomial of theta. So remember, theta of x was, well, if I divided by theta by its derivative at the origin, it was x plus something like e2 over 24 times x cubed, and so on. The coefficients, it was an odd power series, and x's coefficients were quasimodular. And then if I applied the evaluation map, then it would start x plus capital X plus 12 over 24 x squared. And I gave you that formula yesterday, so it's in my notes, but again, I can't keep track of everything. But now I can explain it in a, now I can't find yesterday's notes, so I'll just look here where I do the evaluation polynomial. So the final answer for the evaluation polynomial was that this thing was equal to e to the power x, little x squared over 2 times sinh of little x squared of capital X over 2 over the square root of x over 2. So that looked very mysterious when I did it yesterday, but if you think of this definition, that the evaluation polynomial just consists of looking at the asymptotics when tau goes to 0, then all you have to know is that theta of, now I'll put the tau back in, theta of x tau is essentially, if you take theta of minus 1 over tau and x over tau, this is a modular form of weight a half, then there's some exponential, and then theta of tau x. So the theta function is a well-defined transformation law, and therefore to know what happens when tau goes to 0, using this is the same as when tau goes to infinity. And since the evaluation map is a homomorphism, you can now just read it off immediately and you get this answer. It's a little exercise of 2 minutes. But just to say, if you look at this formula and at the leading term of theta, so theta itself looks like q to the 1/8 times e to the x over 2 minus e to the minus x over 2 times 1 plus O of q. So this part is exponentially small. So the leading term of theta is essentially sinh. And therefore, the leading term up to some shift has the sinh, and that's where the sinh is coming from. So I just wanted to have said that, because yesterday I didn't mention that aspect. I just defined this evaluation polynomial artificially by sending E2, E4, D6 to these polynomials. So it looked a little like a rabbit out of a hat. But we don't actually care about that, meaning this is perfectly good. But the important thing was, as I said, that Eskin and Okounkov discovered that where there is no closed formula, really adequate closed formula, for the full Bloch-Okounkov mapping, so for any polynomial in the QKs or PKs, the full Q series, if you take the X series, there is one, and I wrote it yesterday the way they wrote it, but I also wrote it in a different way. That was the theorem that we had found, and I won't repeat it because I need those notations now again. So the theorem that's in the paper, I'm always talking about the same paper yesterday and today with Chen, Müller, and myself. The theorem that's written in the paper that I'll remind you from yesterday is that this phi of u, x, by which I meant the evaluation polynomial of the original phi of uq, so this is, by definition, this thing is equal to a Gaussian integral, a formal Gaussian integral, where I told you what that means when you have a formal integral y squared over 2, and you put some power y to the n dy. Then this is, this is, of course, a convergent integral. It's 0 if n is odd, and it's n minus 1 double factorial if n is even, if I didn't mess up any factors, but it's something like that. I think it's correct. And so if I write such a thing with a formal power series with coefficient q, I'll still get a formal power series with coefficient q, and whether it converges in any particular sense no longer interests me. So the u, remember, is this multivariable. I still need the capital X of my evaluation polynomial, and then I need a third variable, a small y, that I integrate with respect to. So this was the formula where B was given in 2 different ways. And the nicer way, first I gave it as a big infinite sum. So when I don't care about the other things, I'll just put B of y. B of u xy was given as the sum beta k times the kth derivative of y times x to the k over 2. The beta k are the same numbers that I had, well, I've erased them now, but they were the coefficients of x over 2 over sinh x over 2. So beta k is only non-zero for even k. So this is a power series at x. There are no square roots of x. And tk of y is just the derivative, except that I made a mistake. It's k minus 1 of y, where tk is the kth derivative, but of course ty is the integral. And t of y is defined by t of y. It's defined by the equation that t of y is u of y plus t of y, where u is the generating function of my variables tj. So there's a bijection, of course, between a collection of indeterminates u1, u2, u3, and a power series of one variable without constant term. So you take that constant term, you replace the linear term by, anyway, you just take this equation, and that has a unique solution, which you can write out at the beginning. I think I did write it last time. So t of y starts, I wrote 3 terms yesterday, I'll just write 2 now. It's u2 y squared over 1 minus u1 cubed, and so on. So you have as many coefficients as you want, and now you just apply this formal procedure. So that's, in a way, a very, very convenient statement. And now I want to come to the main statement, the cumulants one, but I have to say one last thing. And the one last thing is this. So again, this was already in the Zagier-Okounkov proof paper we gave. From our point of view, there was a different proof, simpler, not simpler. But here's a fact, so proposition, also due to Zagier-Okounkov, but then, as I say, reproved by us in a different way. If you have arbitrary functions, so if fj is an element of the Bloch-Okounkov ring, let's say it's homogeneous of degree kj, then if I take f1 and I multiply, but don't multiply, if I multiply f1 up to, let's say, fn, so I have n of them, then if I just multiplied them and took the Q bracket, that would be a modular form of weight k, which would be half the sum of the k's. So this thing naturally would be there, and therefore, the weight would be this, but therefore the product would be in M2k, in R2k, assuming that this is even, which I will assume. Okay? So if I had a bunch of elements which are homogeneous and such that the total weight of their product is even, I call it 2k, then if I took Q, it would be a quasi-modular form of that weight, and therefore if I took the bracket of it by what I said here, the evaluation always is a polynomial of degree at most k, where k is that half weight. But now when I take the cumulant, I'm taking an alternating sum, but all of the terms have the same weight, and whatever the weight is, if this is k1, k2, k3, all of the terms here have total weight, the sum the ki, and therefore each polynomial is degree at most k, but the degree of this is in fact no longer k. It goes down, and it goes down by at least n minus 1. It might happen to go down more, and that coefficient might be 0. So this is the degree drop. So for every vertical line that you write, the degree in x goes down by 1. So it would naturally be half the sum of the ki's, but it's actually at most that minus n minus 1. I mean, of course, even if n is 1, it might be smaller. Like I told you before, that the x evaluation of delta is simply 0. So, your function might happen not to have a constant term, and then you might get 0. Okay, so that's important. And because of that definition, we can now introduce our third bracket. We already had the Q bracket. So definition, if fi are as above, so I won't copy it, it's the same notation, then when I put a cumulant, but I'm going to put now capital L. So this L means leading term. It's no longer a variable like x or q, but even x and q weren't really variables. They were to remind you which bracket we're taking. This is the leading term. Then this is, well, it's the limit as x goes to infinity, if you want to do it formally, of the, you take the cumulant, and then you take its x valuation. So I don't know if I ever defined that, but this is, I assumed it was obvious. This is the evaluation of the original cumulant. Right, and we have two brackets, the xq bracket and the x bracket, one into quasi-modular forms and one by composing with this evaluation thing. And now we know that the degree drops, and so if you divide by x to that potential degree, you get the leading coefficient, which will always be a rational number. So this is now no longer a power series or even a polynomial, it's just a number, but that's the number that we really care about. That's the one that dominates the size. And another thing I didn't say, or I mentioned yesterday, about this evaluation polynomial, I just said it in words, is that the degree of that polynomial and its leading term tell you exactly the asymptotics if your f, which is a quasimodular form, has an asymptotic expansion, and you just ask how does the sum of the first n coefficients grow, then it'll be a constant times a power of n. The constant, I think the constant is the degree, but maybe it's plus 1 or something. But anyway, the order of growth and the constant are exactly equivalent to the degree of the evaluation polynomial and its leading coefficient. So there's no point in my writing it out. I'll just get it wrong. But the information about the top term of any evaluation polynomial is exactly the same as knowing how the coefficients grow. And since it turns out that the coefficients we need, because for the connected things exactly come from this, you can sort of believe that this is what we need. So because of that, I could take this theorem, I could try to give a formula for phi, for psi. Well, psi, of course, is just the log of this. But now the one that I care about is psi of UL, which means the leading coefficient. I think I don't have to write it. You take the same thing as here, but just as I do Q, I have one with a capital X, where I take the X evaluation, but then I have one with a capital L, 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 and L, which means I always take the leading term, which means you rescale in the appropriate way and take the limit as X goes to infinity. So that's the one that we really care about for all of these applications, and I want to write that as a second theorem, so maybe I'll erase this definition. So the theorem, there wasn't enough room there. So phi of UL, which I think it's meant to be clear now, but maybe I should write it once more. Well, I can write it with the help of the eraser. If I just change this to L, then you put the leading coefficients absolutely everywhere. But now it's no longer the log, it's some limit of the log as divided after rescaling of the u's, and you let x go to infinity. But this is the definition. So this is the generating function of these leading terms. And so if I know that generating function, I know them all. And the formula is very, very simple. You take the previous formula, and now as you rescale as x goes to infinity, this, think of x as 1 over h, as it just was. You have something of the form, like in quantum theory always, some integral with something over h, and you want to know how it grows, and then what you expect is that the log of this thing is roughly s of a0, where a0 is the maximum of s. So you look at a stationary point. You look when the derivative, or higher dimensional derivative of s vanishes, call the solution of that a0. It's the sort of maximum, the classical position, and then you take the value of this action at a0, and that's what you'd expect. So it's not very surprising, but one has to prove it, that that's exactly what you get here. I made a mistake in this formula. The way I wrote the y here, I did rational coefficients. There's actually what the physicists always call a Wick rotation, but anyway, it's actually iy. So the actual function I have is b of y plus y squared over 2. And so I need that the derivative of b of y plus y squared over 2 should vanish. But now I did get the signs wrong once again, because no, it is correct. So you take the derivative of that, and then the value is simply this. So you just take the power series that I write down, add y squared over 2, because that's the thing that's actually the exponent after this change from y to iy, and you set the derivative of that equal to 0, so b prime of y plus y is equal to 0 at y equals y to 0, and you can compute explicitly where that happens, and that's the answer. So this is the formula how to get the leading term. Sorry? Thank you very much. It's psi, yeah. Phi was the original one, and then I took the log and then the leading term. Okay, so that's, in principle, therefore, solves the problem. Then I still haven't told you, and is it already pause time or not quite? Then I'll maybe tell you very briefly which are the numbers that we actually want. And then after the pause, then there's no more hard work. I can show you how one then actually produces these numbers. So just in a few words now for the original Siegel-Veech story and volume story, I already told a little bit that you have this moduli space of flat connections. And so you have this omega G, which was the flat things, and then you can put various partitions, and the extreme partition, so the biggest stratum, is when you put, there are always 2G minus 2 zeros, which we call n, and if they're all simple zeros, that's the main stratum, that the thing has no multiple zeros, then that's the principal stratum. And so you're interested in the volume of that, the way you normalize the volume. There are various ways from different papers that was explained fairly carefully in both the lectures of Müller and of Martin Müller and Anton Zorich. At the conference I won't, but anyway, it's a well-defined number. And just to tell you as an example, e.g., this was from the paper, if G is 5, so n is 8, then I'm just copying from the table that Martin wrote or projected on the board. I won't write the denominator because it's got lots of digits, but it's completely boring. The denominator is a product of 2s and 3s and 5s and maybe 7s. It's just a highly factorized number. There's a power of pi, which is also boring because there's always a pi to the power n plus 2. But there's an interesting number that in this case it's either prime or nearly prime. There are sort of very characteristic numbers, and there's some normalizing factor that's not very important. So what is this number? That's the number one wants for the geometry that I haven't explained, but that was explained in the conference. But now if you take the numbers, the P2, which remember was actually Q3 up to maybe a factor of 2, or definitely up to a factor of P2, then what I want to do again, for the disconnected coverings, I'd written that you have to take Q3 times Q3, which is up to power of 2. It's P2 to the power 2G minus 2. So you have to take P2 times P2 n times, where again n is 2G minus 2. But here, because it's the connected thing, you want the cumulants. So these are the numbers that you would want for this volume. And I actually have the formula here if you want to, but just to give an example, well, if I write the actual number here, it won't tell you anything unless you're capable, which I'm not, of, there's no point in my writing because there are so many different normalizations. It's essentially the same, up to stupid factors. Stupid means power of 2, a factorial, and a power of pi. But the interesting part, the 2, 3, 3, 5, 7 shows up. If you want the actual formula, I can copy it from the paper, but it doesn't really play any role for what I'm doing since I haven't defined any of these things completely. But just for completeness, here is the formula from the paper. The volume is normalized in the way that was explained by both of those lecturers Wednesday 2 weeks ago. That volume is, if I didn't get it wrong now, it's minus 2 pi squared to the power n plus 1 divided by 2 to the n minus 1. You don't need so many. It's plus or minus pi to the 2n plus 2. I'd already noticed that I could kill something over 2n factorial, and then it's the leading term of the cumulant n times. Whereas in the work that I did with the calculation I did with Kaneko in Degraf's thing, where you wanted simply the number of coverings, that was this thing, but not the cumulant. I mean, you had to take a log also, but it was a different thing. It didn't involve this leading term, the degree drop. Okay, so that's the one you want. And just to complete what I wanted to say before the pause, there were a second collection of numbers that are of great interest to the people studying also the dynamics, billiards on flat surfaces and things like that, on tiled surfaces. There's another thing called Siegel-Veech constant. There are many different normalizations. One is called the area Siegel-Veech constant. And again, if I got it right, but I'm not at all sure I did, the Siegel-Veech constant that one cares about, again, for 1 n times, in this case was equal to, again, I take the case when G is 5 and n is 8. Then from the same table, it was 142,333. This time I can even write the denominator because it's not quite so big. But again, this was in this case, and this was equal up to some very simple factor. And you again take the cumulant, the n-fold cumulant, and then the leading term of P2 L times. But now there's one more term, which is t minus 1. And t minus 1 is the function I talked about last time that didn't, that was not in the Bloch-Okounkov ring, but nevertheless, it's a function on partitions, and so you can still make brackets from it. And it isn't modular, but it turns out that did follow from what I said yesterday. That was the corollary I forgot. I'll say it right after the pause. If t minus 1 had been in the Bloch-Okounkov ring, you could multiply it with anything in the Bloch-Okounkov ring, and this would be a quasimodular form. But in fact, you can't, but you can take an appropriate cumulant, actually not quite. There's a tiny little hitch I'll write right after the pause. But essentially, if you slash it with something in the Bloch-Okounkov ring, that kills some logarithmic term that you didn't want, and then it is your quasimodular. Actually, this is true as it stands, but you want to slightly modify it to make it a homogeneous thing. So you can, t minus 1 itself is not in the Bloch-Okounkov ring, P2 is, but if you take this cumulant thing, then you still are back in the world of modular forms, and you can compute this. So that's, in terms of what I've introduced, these cumulants, these are the two numbers we want specially, and actually we want other cumulants too, but that's would be work for later that we haven't yet finished. So after the pause, I'll tell how these numbers actually come, and I probably won't use up the whole time. So now I'm just make 6 or 7 minute pause till just after 3. And if you have questions, of course. So let me just make one small comment, since there was a question about it that I don't know why you didn't ask it in public, a perfectly reasonable question, which is in this asymptotics. So I have a modular form, it might be e2 to the 7th plus something, and it has its evaluation polynomial, which then would be a polynomial of degree, in this case 7. So it might have some more terms. Like for instance, I could take E4 times E4 squared times E6. That thing has no top term, so it will start, the evaluation polynomial of this thing will start, I guess, not with x to the 7th. Each of these would have an x to the 7th. This, sorry? Oh. So if you took a function like this, you have to be very careful. This actually, the question was about this statement. Think of a quasimodular form that already has some degree drop like we have here. So this is weight 14. So each term individually starts with x to the 7th, but it's smaller, it's x to the 6th. That will be here, if you had something of weight 14, think of the Eisenstein series of weight 14. Its coefficient is sigma 13 of n, which is roughly like n to the 13th. But of course, it's not exactly n to the 13th. If n is prime, it's n to the 13th plus 1, which is substantially the same if n is large. But if n is twice a prime, then it'll be n to the 13th times a factor which is not 1. So even for a simple thing as the Eisenstein series, E14, the individual coefficients do not have any asymptotics. But when you average them, they do. And his question was, here can you also give the subleading term? So here this will grow. If it were n to the 13, which is what you'd expect when you sum, you'd get n to the 14th. But now it'll only be like n to the 12th, I guess, in this particular case, times a constant coming from this constant, some C prime. But what he asked is, can you then give the next term the coefficient of n to the 11, n to the 10? And the answer is no, for the reason I just said. If you change n to n plus 1, you change by one term. They kind of oscillate around. This only works on the average. And if you want to see the whole evaluation polynomial from the asymptotics, you'd have to smooth several times. You would have to take this average and then, like Zagier sums or something, sum it again. So with better and better weighting functions, you can, I think, from the asymptotics of the coefficients, easily produce the whole polynomial by taking other averages. But here it's only the leading term, and it's actually a not completely trivial analytic statement. You have to do a little bit of work to check that. I just mentioned that because it's kind of, just not to make a misconception. So now I want to go back, as I say, you can sort of forget all this stuff about cumulants, because now I have a formula for the cumulants, whatever they were. And I told you that for the numbers that you want for the geometry, there are two specific numbers that we care about. One is the n-fold cumulant of a bunch of 2s. Sorry, I'm using the notation from the paper. somebody should have stopped me. 2 would just be a number, and the cumulative of a number is just 0. I meant P2, but we introduced the abbreviated notation that 2 means P2. So here it's P2, P2, P2. Here I wrote it correctly. Lots of P2s and a T minus 1. So these are the only 2 specific things we care about. And there's this general formula, but you see that since if I only wanted this one, P2, 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 then in this generating function, which I've erased, but it was the sum, remember, it was the exponential of the sum PLUL. So if I'm only interested in P2, I only need U2. So I'll actually be mostly specializing to U is 0, U, 0, 0, 0. But I can't completely specialize like that. That would only give me this one. But here I have T minus 1, which involves everything else. But it's essentially this. I have to take some derivatives in the other variable, but just first derivatives, and then specialize to this U, because I have only one thing in this cumulant that's not a P2. So I'm not going to go into that, how it works, but the main thing will be specializing when you have all zeros. So maybe I'll first do the case without the T1, because it's kind of easier. So if you take the case that I just said, when U equals 0, so U is 0, U, 0, 0. In other words, Ui is delta I comma 2 times U2, which I can then just call U. Then in this case, you can actually work out what B is. So here's just a proposition. Well, it's not even a proposition. It's sort of easy. In this case, I can give B, and therefore from the theorems I told you, you can work out both the leading term here, which is essentially the thing I've done with Kaneko, and the corresponding cumulant things here, which is this new thing. So let me give that formula. But to give that formula, I first have to introduce the Bernoulli power series, which I already gave in my talk at the conference, but I certainly don't want to assume you were there, and I definitely don't want to assume you remember anything. So I'll write it again. So let me first remind you that you have Bernoulli polynomials, bk of x. So first you have Bernoulli numbers that I've used many times. The Bernoulli polynomial is defined either by generating function Bn of x or by bk x to the n minus k. So these are just famous polynomials. For instance, b2 of x is x squared minus x plus a sixth. But I could rewrite this as x squared times 1 minus 1 over x plus 1 over 6 x squared plus it's a power series which happens to terminate. And now you can do the same for, except that is true, but I don't want to do it. I want to put now script b n of x is the Bernoulli polynomial, the nth Bernoulli polynomial shifted by half. So b2, script b2 of x would be x plus a half squared minus x plus a half, so that should be x squared plus a quarter minus a half is minus a quarter plus a sixth is minus a 12th, I think. Okay? So you have these shifted Bernoulli numbers, which turn out to be actually a little bit more convenient. And so this, as you can see, is x squared times an even power series, which here terminates in 1 over x squared. And that's always true if you just take the definition of Bernoulli numbers and remember that all Bernoulli numbers with even indices are 0, except b1, which is minus a half. So this thing starts with x to the n minus n over 2. X to the n minus 1, but when you shift it by a half, it loses the next term. In fact, it loses all of its odd terms. It's an even power series by the standard thing. So in general, if I take script b n of x, then I can write that as x to the n times 1 minus n times n minus 1 over 24 times x squared plus, the next term is 7 times n minus 1 times, it's written n minus 1 again, but I think that must be a typo for n minus 2 over 5,760 times x to the minus 4, and so on. So these are just the Bernoulli, the polynomials here. You can see it's x to the n times the power series and 1 over xk, except the form is slightly different because of the shift. Okay, but now you see that this makes perfectly good sense as a power series, even if n is a fractional number. It could even be a complex number, except for the x to the n. But if n is, let's say, half integer, this would be a Laurent series in 1 over x in 1 over the square root of x or something. And there'd be this part and there'd be this part. So these are the functions we want. So, and I'm particularly going to be interested in these functions when, now I don't know what to, I can erase this now. So we're particularly interested in this for half integers, and in particular I'm going to need the following three. b minus a half of x is x to the minus a half minus 1 over 32 x to the minus 5 halves plus 49 over 6144 times x to the minus 9 halves. The next one is 341 over something, then b 1 half of x. So these are examples, but actually the only ones I'll need. b half of x is x to the half plus 1 over 96 x to the minus 3 halves minus 7 over 6144 times x to the minus 7 halves, and actually plus, not that it matters, and b 3 halves of x is x to the 3 halves minus 1 over 32 x to the minus a half plus, and the coefficients are essentially the same as you see for all of them. There's just some very simple factor binomial coefficient that's changing. Okay, so those are the three explicit ones. And now in terms of those numbers, I'm going to use this. And the capital X, I didn't say it before, but there was a question actually from Paul Norbury in the formula that I raised. At the end, there's no X because I have the leading term. But the leading term was originally the coefficient of the highest power of X. But actually, everything's homogeneous. You don't really need the X. In the function, in the power series B, which in general had a B of u, y, and x, it's homogeneous. If I tell you which monomial I have in the u's and in the y's, you can uniquely say what the power of x is, so you can rescale. And so actually, in the final analysis, I didn't actually say it in this conjecture here, b of y, here is b of u and y, but x is 1. I mean, I've just already normalized. The x is gone. I've rescaled it away. Okay, so here also, we're interested in the function, I'll just call it b, u, instead of u underlined, because it's this particular thing. And again, the y, x is 1, so it's that. So this is the function that I need to apply this general theorem here about the leading coefficients to the special case with 2, 2, 2. So it has to compute this formula, and there that was the nice surprise that it's given by a simple closed formula. I mean, or rather elementary. It's not at all simple. It's got a whole bunch of terms. It's the function b 3 halves evaluated at 1 minus 4uy divided by 4u minus y squared over 2 plus y over 2u minus 1 over 12u squared plus 1 over 24. I mean, actually, all of this junk just kills some terms at the beginning. They're not extra terms. I'm actually removing some terms. So this starts however it starts. Okay? So that's the particular b that I need. And so therefore, to solve everything, I just have to take this function, differentiate it, and add y, and get 0. And so I can get all of my numbers. And so here I can actually give the numbers. I mean, I gave them in my lecture. But here in the other lecture, but I wanted to give it again, if I can. I'm missing the definition. I have the answer. Here we go. So if I send, so corollary, this implies, corollary together with all the stuff I've been telling you, if I let Vn be this number, which is essentially the volume that I was talking about, so it's P2, the cumulant of P2 n times. And also it turns out to be a good idea to put V minus 2 and V0. So remember, n is 2g minus 2. So this Vn is if n is at least 2, which means g is at least 2. But I then also, Vn is V for odd numbers will be 0. And, but I still want V0 and V minus 2, which correspond in some sets. This doesn't make sense, but the number minus 1/24 makes perfectly good sense. And then the theorem, the formula, then I keep permuting everything. I even wrote that out by hand, but I don't know where either. It should be on page 64, but of course page 64 is also run away. 63, 64, where the hell is it gone? Here, 65, there we go. So the theorem then here is that you get it, so that's the theorem. This implies that this is given as follows. So these are the numbers I want. This is the B of uy, which I've now given in closed form in terms of B3 halves, which I both defined and gave you the first few coefficients. And now what I'm going to do is I set x, which will be x of u, so it'll have a double pole, it'll be a Lorentz series, and it's defined by saying that if I take b sub a half of this x, so my u is going to be small, and this is going to be like 1 over 4u squared, if I remember correctly. But u is small, x is big. But in all of these expansions, of course, x is big. We're talking about the expansion of shifted Bernoulli polynomials, here of half integral index, for large x. It's maybe not the same x, but it's some x. So the formula is simply b a half of x is 1 over 2 squared of u. So that defines, since b 1/2 of x starts square root of x, this tells me that the square root of x is roughly 1 over 2u. So x, as already said, will start 1 over 4u squared plus lower terms. And you can compute as many coefficients as you want inductively from this. And then, now that if I have x, I can do very different things. And the simplest is simply to take the expansion of x in terms of u. And those numbers are the original Vn up to a small factor, which is 4n plus 2. But it's important to include v minus 2 and v0 in this formula. So x is given by 4n plus 2 times vn times u to the n plus 1. But there's actually a second formula. If I now took b 1/2 of x in terms of u, it would be boring. It would just have one term, 1 over 2 squared of u. But I can take the next one. So now I've used b 3/2 of x, b 1/2 of x to define x. I can look at b 3/2 of x. And if I look at b 3/2 of x, it's kind of amusing that it involves exactly the same coefficients, just with a slightly different normalization. That's a little exercise. This time it's shifted by a half. So we actually have two different ways of getting the Vn's, either just directly by inverting this series or having inverted by substituting in the other one. Okay, and while I'm about it, I might as well give the last numbers too. So the numbers that we care about, which are essentially this kappa n up to some normalization that I won't even attempt to get right, they are given by the generating function 64. I won't get the normalization right. I think there are no factorials. So if I take, well, the actual number, it's not exactly these numbers. So sorry, kappa n is not this. The kappa n that you need is actually it's smaller than or equal to. And the actual kappa n that gives the Siegel-Veech constant, this is correct for this area constant. But the actual kappa n that we care about is some combination of this for n prime less than or equal to n. But anyway, this is the key number are these things here. Maybe I should actually write down the numbers we actually need. So I'll give the kappa n's as well. And just believe me, these are the numbers we need. So the definition is not interesting, only the answer is interesting. But it doesn't make much sense to give the one without the other. So I take, if n is 0, I have to add 1. But otherwise, well, that's silly. If n is 0, it's just 1. But if n is positive, it's the sum k from 1 to n of 2 to the k times k over n minus k factorial times this maybe I shouldn't even have done this. This is essentially these numbers, and there's an almost similar formula that if you now make the sum of kappa n u to the n, which in this case I can give a few of the numbers. I hope this is the one I gave before. In the table that I raised, there was 142,333. And I'm just showing the cap, as I told you, after some transformation. So it's not exactly the P2, P2. It's exactly this thing. These are the numbers that we actually need for that. But to get them, you need the story with the T minus 1. I'm sorry, it's a very intricate story to tell everything. But the numbers we want are these generating functions. I put them together in a big generating function, k of u, and then the formula for k of u is similar to all of the others, namely, so now that it gives me kappa n and vn. So now I'm giving them all. Kappa of u is given by 2 times the square root of u times k of u is b minus a half of x. So I use all three of these series, b minus a half, b a half, and b 3/2. One of them is 1 over the square root of u. One is essentially k of u. One is the generating function of the vn's. So in other words, all of these numbers I get from this. I just want to say one short thing about the t minus 1 business, since I talked so much yesterday about the TPs, and that's by the heart of the sort of analytic part of this whole proof, or the combinatorial part. So maybe I'll just say that sorry? T1. Well, T1 is not at all interested. You're interested in Tn for n large. Yeah, I mean, TP, or TP tilde, was actually the sum P times Q k minus P, some alternating sum, P plus 1 minus K. So indeed, T1 is Q2 or something. The very first, very small number, there's just, yeah. I don't know, there's 2, 2, 2, 2 we already know. That's the one I gave first. That's the easy one. And of course, one of these numbers is the same. Here I put t minus 1 because it's not really what I want here, but it's what goes into the story. You'll see why in a second. But the actual numbers I need are a combination of ones with higher k. And it's this one, 2, 2, 2, and p, so this is still the cumulant, pk minus 1. So if k happens to be 2 here, then indeed you'd have, or k happens to be 3. If I did it right, then you'll have P2, P2, but it's just one term in a sum. I'm not quite sure what you're asking. The form is here, but T1 never plays any role. This is T minus 1, but I want to say something about T minus 1 because that is interesting. So I told you yesterday that the T minus 1 is the hard part, and that's why we did all that hard work that I reported on yesterday. Here you don't see T minus 1, but believe you, what you really need is this cumulant. But because of the formula I gave yesterday, we had a formula for TP which made its dependence on P obvious when P was a positive odd number. And it was the sum of certain things, and so you can extrapolate. And so at any given level, you can write T minus 1 at that level as a combination of higher T1, T3, T5. And that's why what we actually care about is, believe me, this number. But you can rewrite it, and that's what I want to very shortly show you, how you get information about T minus 1 from the rest. So this is not an important point, but if you kind of absorbed yesterday what the main theorem said, you might have wondered what happens with TP. So yesterday we had these TPs, where P was TP tilde, which was different by TP from a constant. P was greater than or equal to 1 and odd, but it could also be minus 1. It could in fact be any negative number. But if P was odd, then TP tilde was in the Bloch-Okounkov ring. And in fact, it was a specific quadratic element that I just wrote down. Up to a constant, it was the sum, the alternating sum, qk times q p plus 1 minus k, k from 0 to p plus 1. So TP tilde, if p is 1, 3, 5, or 7, is a known object to which we can apply our whole business with these expansions. All of this was only for things in the Bloch-Okounkov ring. But what they needed, that was why they'd introduced that T minus 1 in the first place, which remember was originally the Miller transform of the minus first moment of the parts of a partition. So the original definition of T was you summed 1 over the parts of a partition from 1 up to the length of the partition, but then we showed, well, I didn't show, but I told you that this is also the sum over the cells in the Young diagram of 1 of the Hooke length squared. So this is an interesting invariant, and this is the weight that you have to put on various partitions to do the Siegel-Veech story. Martin explained that very briefly in his lecture. So just believe me that for the geometric application, what you need is t minus 1. But then I remind you what the theorem was, that as long as p was odd and bigger than 1, then Tp is a modular form, and so I have a perfectly good element of the Bloch-Okounkov ring, and I can multiply it by an arbitrary element of the Bloch-Okounkov ring and take the Q bracket. And the theorem that I told yesterday was that this thing had a universal form, namely there were certain operators, it doesn't matter at all what they are, it's explained yesterday in a lot of detail, but these things are this thing is in the Bloch-Okounkov ring, and it's the original weight of f minus I minus 2j. So whatever I'm doing, although it's apparently an infinite sum, it's actually a finite sum. And then the thing you had to put here was the jth derivative of the I plus p plus first Eisenstein series. So this is a finite sum. And so when you compute the coefficient of q to the n in this, you'll get, for a given n, like n is 11, then you only need the coefficient of this up to 11, and they're just some numbers that are fixed by f and the I and the j. And you need the coefficient of this up to n to the 11. But of course, gk, or well, gi plus p plus 1 j is up to a constant, which is 0 unless j is 0, is just the sum d divides n it's the sum over n, bigger than or equal to 1, q to the n. And here you have d to the n, and then you have d to the weight minus 1, so I plus p, and then you've differentiated j times. So we know the dependence on n for a given n, if I'm only interested in 1q up to q to the 10th. Then if I look at the coefficient of q to the 10th in this thing, I only need the coefficient from 1 up to q to the 10th in these. That's a finite list. And in these Eisenstein series, but then this n also goes up to 10, and so the d also goes up to 10, and so the whole thing, you see that the coefficient of q to the n in this thing will be some linear combination of 1 to the power p, I mean d to the I is also fixed, of 1 to the p, 2 to the p, up to n to the p. Right? It's a specific linear combination. Just finitely many terms, and this is for all p. I mean, you could say any numbers of finite linear combination of any other numbers in Q. But what I mean is that as p varies, you fixed your f, it has some weight, so there are only finitely many i's and j's. So up to q to the 10th, or up to a given q to the n, only finitely many things play a role. And here the dependence on I and j is universal, and the d to the p only involves numbers which divide integers up to that n, and therefore themselves are less than or equal to that n. So that's a finite linear combination. You can do that for infinitely many p's. The t minus 1 is defined by the same function as all the others. It's a perfectly well-defined function. It has to fit this extrapolation. So the result is we now know what t minus 1 f is. It's given by exactly the same thing, but you put here 1 inverse, 2 inverse, and so on. But 1 inverse and 2 inverse means it might involve the integral of E2, which is log of eta. But that's exactly t minus 1q. So if you take the simple cumulant, that's what I said before, and then finally there's one other thing, I think there's an E2 over 24, or a constant, you have to subtract fq itself times something, maybe E2, because of the fact that actually in this theorem it was Tp tilde, which was Tp plus a constant. And you have to do that also for p equals minus 1. So there's one extra term that I could look it up, 1/24 or something. But this new modified, so corollary of all of this, is that if I define a new bracket, then if I have something in the Bloch-Okounkov ring, and I take the product of that thing with t minus 1, which had no reason to be quasimodular, but I take the Q bracket of that, it doesn't have to be quasimodular because this is not in the ring. This is quasimodular. This actually isn't. This is simply up to sign. It's the log of the product 1 minus q to the n, maybe with a minus sign. But this difference is quasimodular, and if you subtract something here that I have written down, I can, just for completeness, I can write it down correctly. It's simply, well, well, it's not exactly right, in fact, so just as well that I looked, it's 1/24th, but here you have to apply a derivative d2, which I defined yesterday, I won't define again, but it reduces the weight by 2. This whole thing will be a quasimodular form again, and what's more, again, at the same weight. So that's a very nice theorem that we don't know any elementary way to prove at all. We need this entire thing that otherwise we don't really care about, this entire structure here, in order to get that. And I can actually give the formula for it. So the formula for this is exactly the same as the other formula. Namely, there's some universal linear operators, rho ij star, which go from R to R. And you take the Q bracket and you multiply by exactly the same as before, but now the P plus 1 has gone away. P is minus 1. So it's this, and rho ij star is simply the old rho ij plus delta I, comma 2 of rho 0, comma j plus 1. This must be an I. Yeah, it is, I, comma 2. So we slightly changed the complicated operators I had yesterday. There's some other operators, but those are really details. So there's a universal formula again for this as a combination of Eisenstein series. But now we don't care that it's universal because this is just some complicated thing. Before, the universality was that the dependence on P was always the same. The P only entered through the indices of Eisenstein series. Now P is fixed anyway, it's minus 1, so this is just some formula. But the point is it is a quasimodular form. And that's the one to which we're going to apply. But then you see by running back through this, to do this extrapolation for a given coefficient, you only need finitely many of the T1, T3, T5. And that's why the thing I really needed, the T minus 1, could be re-expressed in terms of the things here with pk minus 1. And there's a calculation to be done there, but that's the result. So that's how the whole thing works. And I've now said everything important, but since I still have a little bit of time, I want to make one final small collection of comments. So this is the second digression in this course. Today I told two things that have nothing to do, except that we needed them, but that are not just part of this whole story of Siegel-Veech and volumes and so on, but much more general. One was cumulants, which is this very nice general story, how to make these kind of alternating sums when you have a map from one ring to the other. But the other thing we need, I'll now come to, and I'll spend the last maybe 10 minutes on that, and then I'll stop a little early. We now have complete formulas. So as I explained here very briefly, from this formula we know how to compute, so this part here is the cumulant, just the double cumulant of T minus 1 with F, but then by the inductive formula I showed at the beginning, you can take a successive cumulant of T minus 1 with any collection of things, and that will be something that has a quasimodular expression. And then all of those things we can now make the corresponding generating functions. If you do this when F is essentially P2 slash many times with itself, then you will get just, in this general theorem, you'll get the B where U has been specialized again to 0, U, 0, 0, 0, because I only have P2. And then you'll get that special B of U that I erased here, and you'll get these special things involved in B minus half, B half, and B 3 halves. Now we know the leading term. We know the generating function. But we don't care about the generating function, except I cared about it because I like combinatorics. But remember, the reason we wanted these coefficients was not because somebody wants to count exactly how many squared tiled surfaces there are. They want to count it asymptotically because these things become dense, and that gives the volume. So the final application is, what can you now say about the size of this Vn, which is some kind of a volume, and this cap n, which is some kind of a Siegel-Veech constant, for n large. And remember, n is 2g minus 2, so for g large. And there were in particular the conjectures of Eskin and Zorch and various other statements that one somehow wants to understand for large g. So now I've erased the proposition, but maybe you remember the essence of the proposition was that using these three completely explicit power series whose coefficients are just Bernoulli numbers, by inverting one of them and either just looking at that directly, you invert this one and look at those coefficients, or you take that inverted thing and substitute in these two, you produce three different power series in U. Two of them give you the Vn's, one of them gives you the cap n's. So we now know a closed formula, and I wrote an example with that 142,000 something. You can compute this way, for instance, 550 or something of these coefficients. There's now no problem computing lots of them. Before it was very slow because you had to compute the whole thing for the whole genus. But we don't want to compute up to g equals 50. We want to compute up to g goes to infinity because we want the asymptotics. Sorry, we don't want to compute for g is infinity. That's not what I mean. Well, we want that too. Sorry, the asymptotics already does come from this. It's because of the asymptotics that I told that these leading coefficients give the volume. So that part we've already done. So Vn, again, is roughly the volume of this omega mg of 1 to the nth, and kappa n is roughly this C area constant or some modification of it. So for that part, we already used that these things are the leading coefficient here, and so I used this general theorem about leading coefficients that I had to invert some power series and solve an implicit equation. That's what gave these things. So that gives the number for a given g. But the conjectures that I mentioned, in particular of Eskin and Zorich, are about the asymptotics of these numbers. So this is equal up to some simple constant, powers of 2 factorials and powers of pi. But the question now is what happens if n is very large? So first I can just write out the answer because it's just an answer, it's just a formula. But then I want to say a few words about how that comes. So first of all, as I said, let me just give the actual answer, which is written down, so I should be able to just copy the actual asymptotic statements. Now I'm not sure in what language, whether it'll be for the volumes in the original form or for the modified one. I guess I have them both here. So let me write V. So this is a slightly renormalized volume. It's a very, very tiny factor from the original volume, but it's a factor such that the conjecture, I mean, this is a special case of the conjectures that one had by Eskin and Zorch. They had a much more general conjecture for arbitrary things, and the conjecture was that this one should be asymptotically equal to 1. So this V, which is the volume I talked about before, is slightly renormalized. Well, in this case, it's just 2 to the n minus 2. In general, you have to take the product. If you have m1, m2, it's the product of the mi plus 1 divided by 4. But here it's therefore 2 to the n over 4 times the previous volume. But this is the Eskin-Mazur-Zorich volume. So this is just a very, very simple multiple of the previous Vn. But the point is it's normalized in such a way that the conjectural statement was that it tended to 1. So what we wanted was that this was equal to 1. And the theorem is that this is true. And in fact, V of 1 to the nth has a complete asymptotic expansion in G, of which the first first 3 terms are this, and you can compute as many terms as you want. So this is a power series in 1 over G, whose coefficients are polynomials in pi squared. So that's a very specific coefficient. And again, if when you do all the normalization, you take out all the junk factors, then there's only one way to make it 1. And if you take the way that's supposed to make it 1, that is what the conjecture said should be 1, and here's the rest of the expansion. And exactly similarly, I don't even know if it's really worth writing it out. Well, here I can write it in the notations of the paper, but I'm not sure I ever defined. So the C area constants of omega G, again, the principal stratum, that was supposed to tend to 1/2, and indeed it does. And the next coefficient of 1 over G is rational, and the next one is rational. So if you were an engineer, you might say it's in Q of 1 over G, but in fact it isn't, because the next one, coefficient of 1 over G cubed, is 4 pi squared plus 75, and so on. And this again is a power series in 1 over G whose coefficients are polynomials in pi squared of some degree, which is always, after the first one, it's always 2 less than this exponent. So for G to the 4th, it'll start pi to the 4th. So these are explicit formulas, and as I said, that was actually the goal. The original goal of the whole thing was to get an explicit closed formula for these numbers Vn and kappa n, so up to normalizations. There are these 2 numbers that you could compute a whole lot of them, and then in particular try to prove something about the asymptotics. So I've told you before how we got the Vn's and kappa n's in the form of generating functions, But now I want to say just a few words about how you deduce from that the asymptotics, because it's very amusing. So how did we get, once we've gone through all this business, Bloch-Okounkov, quasimodular forms, asymptotics at the evaluation polynomial, the asymptotics of quasimodular forms at 0, everything else. But what are the final ingredients in getting, just the elementary ingredients, so the final recipe to get these numbers Vn and kappa n? Let me summarize. First of all, we have explicit power series which in the particular ones we needed, they're still written there, were b minus a half, b a half, and b 3/2, which were power series roughly in 1 over x squared and then multiplied by some simple power of square root of x. But then, remember what we did. The b that I needed for the general theorem was the b of u, so u1, u2, u3, and so on, and there was a y and there was an x. And then I specialized to x is 1, and I specialized to all of the u's are 0 except for the second one. And then I wrote this as b, I think minus 3/2, there was a factor, times something, plus something. But to get the b 3/2, I had to, so that was the b. And then according to this theorem, I have to take b prime, and I have to solve implicitly the equation b prime, where b prime plus y is 0. So I have to solve an implicit equation. But the b itself was given by the sum beta k, and then the k minus first derivative of another function t. And t itself was given by, I think it was this, t of y, it was u of y plus t of y, where in our particular case, of course, we know what this thing is, because it's just u times y plus t of y squared. So that in this particular case, it's a quadratic equation, and t of y is explicit, and that's why we could work it all out. So what are the ingredients? Once you have this, you use operations on power series. And the operations you need are products and quotients. Then powers, you could say power is a special case of products, but also the negative power and the 1/2 power and things like that. So you have to be able to take power series, you have to be able to multiply power series, you have to be able to divide power series, you have to be able to take powers, including the reciprocal and the square root, but this is products, quotients, but then you want to take inverse power series. Of course, you can only take the inverse power series of a series that has no constant term and starts with x times a non-zero constant, but that's part of what we did, because the definition u of y was given by something, but you have to be able to take the inverse power series. Here you don't really, because you can solve by hand, but then you have to solve this thing, and this is again an implicit thing, so it's also an inverse power series. And then once you have the y0, which you get from this, you have to substitute it back. A substitution of one power series in another, where, of course, again, you can only substitute one power series in another if the one you're substituting has no constant term. It has to start with x, or a higher power, maybe. And then at the very last stage, you take the nth coefficient, but we don't actually want the nth coefficient, because that's the algorithm to get the Vn and the An. But if I want the asymptotics for large n of Vn Kn, then we want the asymptotics, the large n asymptotics of the nth coefficient as n goes to infinity. So the question is, to what extent can we do this? Just if you give me some nice explicit power series, and you allow standard operations that we all learn in high school and in college, that you can multiply and substitute and so on, but can I then expect to get asymptotics for the coefficients? Well, it's a very, very natural question. It comes up everywhere in mathematics. And the answer is, in general, no. There's absolutely no way. And if you take a really stupid thing, and take log of 1 plus x, the coefficients are plus or minus 1 over n. But if you take the inverse power series, it's e to the x minus 1. The coefficients are 1 over n factorial. They have completely different types of growth. And if you take something slightly different, let's say I take x plus x squared minus x to the 7th. Well, the asymptotics to the coefficients of that is just 0. All the large n coefficients are identically 0. But the inverse power series is something or other. It's certainly not 0. The answer is no, you cannot simply, well, sorry, the other thing is, of course, you know the beginning. I mean, I gave you the first few terms. So you start with power series that you know in two senses. To know a power series, in my sense for today, to high accuracy, let's say to 10 degrees of accuracy, means I know the first 10 coefficients, might be the first 20 or the first 10 over 2, but O of n coefficients at the beginning. And I know the nth coefficient for n very large as a power series. It might be, for instance, 1 over n factorial times 3 to the n times n to the minus 5 halves times 1 minus 7 over n up to 11 over n to the 8. Then I would say I know my thing to 8 degrees of accuracy. So if I know the asymptotics of the general coefficient to, let's say, 8 orders in 1 over n, and I know the first 8, or maybe 2 times 8, O of 8 coefficients, then I'd say I know that power series to order 8, or to order 100. Now the question is, if all of my input, I start with finitely many power series like these, which I know in that sense. I can compute the first coefficients, and I know the asymptotics. Here, there's no problem. I gave you the first coefficients. You can get 100 on the computer. And the asymptotics, remember, it was some Bernoulli number. And Bernoulli numbers, we know the exact asymptotics to all orders. So in that sense, here I know the input to any given order. If I need 20 terms, I know 20 terms. But the question is, if I start with power series that I know to order 20, meaning the first 20 coefficients and 20 coefficients of the asymptotic expansion of the nth coefficient, can I then, if I combine them arbitrarily, products, quotient, multiples, inverse, and so on, get any information at all, the same information about the final one? Of course, I can get the first 20 coefficients. I just do the thing. But about the nth coefficient, the asymptotics. And the answer is amazing. It's the exact opposite of what you learned in school. School meaning, up to and including graduate school, but, baby, kindergarten. What you learn is that a series like x to the n over n factorial is real good. Great. It's called an entire function. It converges for absolutely every x. Those are the best. And then you have things like, maybe 3 to the n, x to the n. That's pretty good. It's at least an analytic function. It has a finite radius of convergence, here a third, but at least it's a function. You can talk about it, right? And so this is called entire. This is called convergent somewhere. So this convergent everywhere. And then, when you go to graduate school, then they tell you, sometimes in mathematics, you'll meet horrible things like n factorial x to the n. And then you're supposed to throw up both your hands and maybe even in the other sense, and this is really awful. So this is called rapidly divergent. But now let's say that we're real gluttons for punishment, and we say we want to be even worse than this. Let's consider series like n factorial to the squared times x to the n. This is really very rapidly divergent. So by very rapidly divergent, I mean like n factorial squared, or at least n factorial to a power that's strictly bigger than 1. So believe it or not, I don't like this. It's not divergent enough for me. Very perverse. And now comes the theorem. Completely surprised we found this, and we couldn't find it in the literature, and it took actually quite a bit of effort to prove everything. So the paper ends with an, I think, 9-page appendix that, to make it very clear, it has nothing to do with the paper. It actually follows the bibliography. So it's really separate, like a paper by some other people we don't want to know, but actually it was Martin and me. And in that paper, what we show is for this world of very divergent series, like n factorial squared, that series is closed to any given order under all of these operations. Once it diverges fast enough, then when you invert a power series or substitute one in the other, the only things that contribute are the last terms that you see. The others, the previous terms, when you get to the 100th term, the 99th is much smaller, the 98th is yet much smaller. So you only need a little neighborhood of 100 to see what's happening, and you can invert everything using Lagrangian interpolation and so on. So it turns out, if you're in this very good world where things are really horrible and it diverges like, so when I say n factorial squared, of course, I could also put n to the 2n or 2n factorial. But what I mean is n to the power, well, e to the power 2 times n log n. But 1 times n log n wouldn't be good enough. It has to be strictly bigger. And now you see all of these do it, because this thing is Bernoulli numbers, but the Bernoulli numbers, they grow like n factorial, but the odd ones are 0. So they indeed grow like 2r factorial. And then we're inverting, substituting, and doing it. So we're exactly in the world we could apply these general theorems. And so at the end, you just apply the theorem and you write down the asymptotics. But it only worked because it happened. We had no control of these series. They turned out to be whatever they were. If it had been n factorial, it wouldn't have worked. If it had been conversion, you couldn't have done anything. You wouldn't have a clue, unless, of course, it were a function you happen to know in closed form. But nobody knows the function you get when you put the inverse of that into that. These are unknown functions. But because of this very amusing thing, you have this principle that, for the point of view of asymptotics of series, the worst are the best. So maybe I'll end with that. The worst are the best.